So in the next session at GroupBy, Derik Hammer, who has just, talk about cool last names. Derik Hammer is going to be talking about always-on availability groups. So take it away, Derik.
All right, thanks, Brent. I appreciate it. All right, so hopefully you're at the right session, architecting availability groups. As Brent mentioned, my name is Derik Hammer. I'm a data platform MVP and on the Century One Project Advisory Council, friend of Redgate. But what really matters is that my career has been mostly in the database operations or production DBA area, focusing a lot on high availability and disaster recovery. I've just had a few short stints as a developer, and right now I'm actually working as a manager of database architecture and design for Subway. So a lot of this session is about my lessons learned in the past from when I first had my first production availability group cluster back when version 2012 was the first feature, and then working up till current. So what are we going to talk about today? I'm going to cover 4 different architectures of how you can set up your availability group, working from simplistic up to a more complicated scenario. And then I'm going to cover a couple of the highlight features of availability groups, specifically read-only routing and multi-subnet failovers. This is mostly going to be like a design concepts and features talk with some lesson learns mixed into there. It's not going to be a how-to. Also, availability groups is a very large talk. I wouldn't be able to get to everything within 60 minutes. So there's a whole list of things that we're not going to be able to cover today. We're only going to touch lightly on distributed availability groups. We're not going to be talking about basic availability groups at all, which is the replacement for database mirroring effectively. And we're not going to get into anything with Linux. So availability groups can run on Linux, they can run cluster lists, they can run without domains with SQL Server 2017 and Windows Server 2016 features that have come out, but we're not going to get into all those. So we're going to scope pretty much everything today about running availability groups within a Windows failover cluster and some of the more traditional, based on the version orders that we've gone through since 2012, methods of doing availability groups. So let's talk about the most simple architecture you can possibly have, which is just 2 servers in the same data center. This is inside a single Windows failover cluster. And what you're trying to accomplish is duplicating your data. That's the heart and soul of an availability group, is the fact that you're going to have 2 redundant and identical copies of your database. So what we have here is 2 servers, and those servers can be physical, they can be virtual. It really doesn't matter as long as they're physically separate. So that's kind of the first key tenet of architecting an availability group, is to make sure that you actually have the redundancy that you believe you have. If you have 2 virtual machines, they're running 2 different replicas, but the way that the hypervisor's DR features are set up allows for them to live on the same host at any given time, then that defeats the purpose. So you want to be careful to understand that when you're duplicating something for an availability group, that whatever it is truly is on separate physical hardware. So you would need rules within your VMware clusters, for example, to make sure that your VMs never land on the same host together in the event of a host failure or a load-based migration. That extends to your I/O layer as well. So you see here I have 2 disks in the diagram. They're showing them as local. Whether local or remote doesn't really matter as much. The key tenet is, once again, understanding that your duplicated data is physically separate. Now, I know a whole bunch of SAN admins out there will say, well, my SAN is redundant, therefore it's not a single point of failure. But I've also personally lived through several SAN outages, whether it was a bad firmware upgrade or whether there was a massive power outage or something like that. So please don't treat your shared storage as if it is truly redundant. Putting both of your replicas on the same physical disks is just as bad as putting both of your VMs on the same physical host. You never want a situation where your availability group can go down because of you losing any singular thing. So in this architecture, really all we have is HA. We've got high availability, which is typically described as the fast and highly responsive failovers. There's synchronous commit between replica A and replica B. And what that means is that it's replicating data from the primary to the secondary, and it's doing it in a manner in which it can guarantee 0 data loss. The way it handles that is the application will send a transaction down to the primary, and then as it's writing log blocks, those are being sent over to the secondary. At the end of the transaction, when it commits, and the secondary has to harden its blocks, which means it has to be able to make sure that that data is durable on the secondary. It'll reply back with confirmation that these blocks have been hardened, and the primary can then allow the commit to complete and reply back to the application that the transaction has been completed. Because of that, you know that at any given time, if replica A, the primary, were to drop out, whether the server crash, whatever the case may be, you know that only one of two things could have happened. Either replica B has all the appropriate data for it to finish its redo phase and you haven't lost anything, or the transaction never committed. If it didn't commit, the application gets an error because of the loss of the server, the connection is going to die anyways, and the application will know that it never successfully completed that transaction. Therefore, it can do whatever appropriate retry logic or whatever error handling is built to the application from there. But at least with synchronous commit, the application is never left into a situation to where it was told a transaction was completed and then it lost that data. Because of this, you can achieve automatic failover. It's a simple flip of a switch effectively, whether you want manual failover or automatic, and you can only do automatic failover when you have synchronous commit. And that's because effectively Microsoft's not going to put a feature in there that allows you to automatically have data loss. That would just be disastrous for all of us. So what we have here is successful high availability at our database level. And I want to be clear about that because these are user databases that you're grouping together. One of the great things about availability groups is that you can have multiple availability groups on the same instance because you can put different sets of databases into different groupings for failover. And then if your application relies upon 3 databases, for example, then all 3 of those can fail over together. And it's a big unit that goes back and forth in order for your application to never have them on separate servers, and you don't have to have the entire instance move. For example, this is just databases. Your other instances is online and active the entire time. What this does not include, however, are system databases. So master, model, etc. MSDB, for example, those ones are not being replicated, not part of availability groups, which means that right off the bat, even with this very simple architecture, you're going to have to handle synchronizing your server level objects yourself. What I mean by server level objects is you're going to have to manage logins, you're going to have to manage credentials, SSIS packages, SQL agent jobs, certificates. All of that's going to be on you as DBA to handle. Now, as we continue through the presentation, I'll mention some resources and such about automating that, but I want to make it very clear because unless you have a very well-tested failover plan, you tend to find out during a failure that you moved over to your secondary replica and that new login that was added last week doesn't exist on your secondary, and now your entire application doesn't work. So you don't let your instance or server level objects induce a secondary functional outage when you're relying upon a high availability feature. So it's a big asterisk there. So as I mentioned, this is the simplest architecture. We're going to make it a little bit more complicated now. The second one is including a secondary data center into the mix. So now we have quadrupled the number of servers that we needed for the original application, and the same thing with our disk. So a big highlight is I've had several different fights in my past when using availability groups with storage admins about the amount of space that's being used by duplicating this data so many times. I know everybody says storage is cheap, but as soon as we say storage is cheap, then people start talking about solid state drives and Fusion IOs and all the new expensive high performance SAN arrays, everything like that. So whether disks are cheap or not, it is a factor. It's a capacity, and it's going to be a cost of your HADR solution. So it should be considered and acknowledged up front what that looks like. So in this area, we now have 4 copies of our database. We have 4 servers. And ideally, all of these servers are going to be identical hardware. It's not a good idea to ramp down your DR site because the workload that's running on your primary eventually will have to run on the secondary no matter which one it is anyways. On top of that, you need to make sure that you're keeping all of your replication in sync and you're not inducing performance problems from that. The way you do that is by making sure that your secondaries don't have lower performing I/O subsystem. They don't have, fewer CPUs, because those are going to be needed to process the replicated transactions that are coming in and redo all those log blocks. So do not undersize any of your servers. It's ideal that all of them are identical in almost every way that you can possibly make them. So now there's a bunch more icons on this diagram from the last one. I'm going to start with the subnets. So now we have two subnets here, and the reason for that is because this example has to do with two data centers. So this throws into the mix the concept that you're going to have two IP addresses as well. And that's where the ear comes in the top. The ear is meant to represent the listener. I didn't put it in any specific spot in this diagram because the listener itself flows with the primary. The listener is actually in this example, a Windows cluster resource that is effectively a virtual network name that has n number of IP addresses with only one of them online at any given time. This is important because the listener is going to follow the primary. And whenever you connect to this singular virtual network name, you'll be able to get a different IP address if you were to fail over from, let's say, replica A to replica C. Now, we're going to talk a little bit about the connectivity of that and what the performance looks like of the listener in a few slides. But for now, let's switch over to how replica A can actually replicate to replica C. And we're using async commit in this diagram here. And what asynchronous commit is extremely similar to what I just mentioned in the last slide about synchronous commit. The primary difference here is that once the transaction commits successfully on the primary, rather than waiting for all of the secondaries to harden their log blocks, instead what it will do is immediately reply back to the application that the transaction has been committed, and that transaction is good to go. This is where potential data loss can come into play if you have to do a DR failover. Now, HA is fast, automated, try to be as available as humanly possible. Disaster recovery is typically a much larger event that has a much larger RTO, a recovery time objective. And then that means that manual intervention is typically expected in those situations. So with asynchronous commit, what you're forced into is a manual failover because of the potential for data loss. And you're going to have to acknowledge the potential for data loss in order to do the failover, either via T-SQL or through the wizard, through Management Studio that can handle this. You're going to have to check a box, or you're going to have to type in a parameter at the end of the T-SQL that acknowledges the potential data loss. And it's going to force you into the manual situation there. But this is meant to tell you that there could be data loss, not that there actually is. So one thing that I've had to explain a lot in the past to people is when they've looked at different statuses in the availability group and they're like, well, I turned off the application, I waited an hour for everything to synchronize, but it still won't let me fail over with zero data loss. And it's like, well, technically speaking, you will have zero data loss in that situation. If there hasn't been a transaction for over an hour and that has been successfully replicated over to the secondary, then it is a zero data loss failover. However, the feature is going to force you to acknowledge that you are identifying that for yourself. There's nothing within the availability group that's telling you the zero data loss. You can query the DMVs and understand it, but you're kind of acknowledging that that's on you. So it forces you to still go into that situation. So now that we have our potential for failover and we have all of our servers, I want to highlight again that you now have 4 different places to synchronize all of your server objects. This is another reason why it's really important to automate it so that this isn't a maintenance hassle of, you don't want to get the situation of every time somebody puts in a ticket to have a new login created in a database that you now have to create it in 4 places. Because inevitably, and probably sooner than later, you're going to have human error. Somebody's going to miss a server and you're just going to fail over to that box, 6 months down the line and wonder why your application is either only partially functioning or not functioning at all. So now this is the architecture that I like to recommend. So we're going to dip a little bit into ones that I find are less favorable just next. So we want to remember this one as kind of my ideal HADR solution with availability groups.
Now, Derik, I do have a few questions here from Brian, and he was asking, would you ever consider having smaller hardware in the DR location in a public cloud scenario where you are doing a manual failover and could dial up the hardware before the failover?
So the problem that I would see with having lower hardware in the public cloud when you're not actually running a workload over there is the synchronization. I've had to troubleshoot a lot of situations to where we were wondering why the secondary was always so far lagged behind the primary. And common reasons for that include network throughput, but it's not applicable to this question here. So then another common one is the I/O subsystem. You know, if you've ratcheted down in the public cloud and all of a sudden you have less IOPS to work with, your primary is still going to burn through transactions with its full scale of IOPS, and it's going to do whatever the primary can do. If you have enough data throughput, the secondary is not going to be able to harden those data blocks as quickly, and you're going to get a backup. In addition to that, if you scale down the CPU too much, then you're going to have issue with the redo when it's trying to redo those log blocks on the secondary side. So if you know that your throughput, your primary data throughput is small enough that by reducing the secondary, you can maintain your appropriate recovery point objective, which is, recovery point objective is how much data you're willing to lose in a potential failure. So if you know that you're going to be always 10 minutes lag behind because you've, you know, undervalued your secondary site, and you're okay with that, maybe you're okay with an hour and this is only 10 minutes, then that's technically okay, but I'm still not going to advise it. And the reason for that is there's a lot of unexpected things that can occur that can just destroy your recovery point objectives. For example, let's say normally you have intelligent index maintenance that occurs in the weekends, and it only usually rebuilds 1 or 2 indexes a weekend. So you get a feel for what that data replication throughput is on a weekly basis. But then something happens. You do a deployment that does massive changes to your tables, and then that weekend maintenance means all of your indexes get rebuilt because they got heavily fragmented, or whatever your criteria is for deciding whether those indexes get rebuilt. Well, then you're going to have a sudden surge of data throughput that you weren't expecting. You're going to lag behind far longer than you expected, and then if there was a failure any time within that window, now you've just blown away your recovery point objective. So be very careful. Technically you can do it. I have been put in situations where I was forced to do it, where I just couldn't convince the right people of the right thing to do. But my standing recommendation is to always match hardware the whole time, especially if you want to leverage some of the other features like read-only routing that we'll talk about on the second half of the presentation.
Now, Emily is asking, a little confused. I thought the listener would do auto failover. Is it because they are in different subnets, so you will need to do the manual failover? And a follow-up question from her as well is, can we use the replica to offset certain jobs to do backups and or read of databases? Now, if you're going to cover that in a future slide deck, you could leave the answers towards that portion of your presentation, but that's Emily's question.
Okay, so I'll give you a short answer and then tell you, yes, there's more coming in the next few slides. So the short piece that I'm not going to cover in future is that the listener itself is a virtual network name that is important during the failover, but the reason that you can't do automatic has nothing to do with the listener. It has to do with the synchronization setting. So the fact that you're using async, or if you're using synchronous but you've chosen to not allow automatic failover, that's an option as well. In either one of those cases, that's what's preventing you. The listener, the mechanism isn't really the problem. In theory, if you were to use synchronous commit between your two data centers, which I'm not advising because of performance, but you could technically do that. That would enable you to do automatic failover across data center, and the listener is not going to stand in your way. The subnets are not going to stand in your way for that. The main reason I advise against it is because typically your DR center is hundreds of miles away at a minimum, and the network latency involved there can cause performance penalties through application. Remember, your application has to wait for the secondary to harden all those log blocks before it can say it's done. So a transaction that might be sub-second on the primary but then take another 10 seconds to get to the secondary will make the application wait 10 seconds instead. So be careful about your performance in that regard, but technically it can work the way you want. And as far as the read-only routing and backup offloading, we'll talk about that a little bit later.
So I'm guessing you're also going to cover maintenance and patching in a future slide.
So actually I'm not. Maintenance and patching is something that if we have time, I'll definitely talk about, but I feel we're going to run out of time with the content that I have.
Sure.
Okay. All right, so the architecture that we left off on here was blending two different always-on features. I know some people cringe when I say always-on, but the marketing name for failover cluster instances and availability groups is actually always-on, and you can layer them on top of each other. So I mentioned a moment ago that the previous architecture is my preferred, and the reason is because we're getting into layers of complexity that I personally don't appreciate when I'm troubleshooting an outage or a failover of any type. So in this area, the reason that somebody would use this is if they get put into the corner to where they cannot have the quadruple size of their database. You know, so if you've only got a 100 gig database or something smaller than that, having 4 copies of that is usually not a huge thing to sell people on. But if you're talking about multiple terabytes, like one system I have today, not a single database, but within the availability group itself is 13 terabytes of data. In those situations, trying to tell people that you need 4 copies of that becomes a much bigger discussion where some of the dollar values they're talking about actually a little bit more reasonable. So if you get forced into the situation to where you're not going to be able to have 4 copies, then this is a good solution, where instead you are relying upon your SAN, so you're going to go back to relying upon the redundancy that the SAN admins are advocating, and you're going to only have 1 copy of your data in each data center instead of 2. And what you're relying upon here is the failover cluster instance feature, which is a service availability feature, meaning if the SQL service or the server itself has a problem, then duplicate copies of those services will come online on the other server. But they're going to utilize the exact same data. So this is a zero data loss situation that allows or has only automatic failover because of the fact that they're both right in the same place. So it's impossible to have ever had a situation to where data wasn't replicated. So on this diagram, replica A, for example, could move back and forth between the servers within its data center. Replica B could move back and forth between its data center, but it wouldn't cross data centers. And you're using an availability group for the database level replication to be able to asynchronously commit between the 2 data centers. Again, I'm recommending async because of the performance, the typical latency, the network latency that you would have between 2 different data centers, and that will be a manual failover. Now, once you layer availability groups and FCIs on top of each other, you completely lose the ability to do an automatic failover on AGs anyways. So a moment ago I mentioned you could, in theory, use synchronous commit and do an automatic failover across data center. You won't be able to do that as soon as you use FCIs. And the reason for that is because FCIs are already doing automatic failovers, and you can't have 2 different competing features trying to handle the failover situation. So as soon as you layer them on top, the AG knows it's on an FCI, and it disables the ability to do automatic failover. So in this situation, you're saving some money, but you're adding a lot of complexity. As soon as you have a failover, you've added a second feature, a second set of logs, a second potential chain of events that could have happened in order for you to troubleshoot. So if you're saying, why did I fail over? What's the problem with this? It adds a lot of hassle. And if you're in an emergency situation, you know, like a production failover, for example, you may not have the time to properly diagnose everything. So it's one area that I don't enjoy this, but it has been something I've had to do in the past because of the limited space on disk. Another thing that I'll mention is the fact that the failover criteria is different between FCIs and AGs. FCIs are service level, so you could have your database completely unusable, but the service is running, and you're not going to get a failover. So with different versions of SQL Server, the criteria for what can induce an availability group failover has changed. It's improved. It's gotten better and better and closer to the database health with every version as it's continued. So I won't cover the full spectrum here, but what I will say is that FCIs don't do anything for the database level. So while you would have previously been able to fail over automatically within your data center because of some database level fault events with the previous architecture using just AGs, in this case you won't. It'll have to be something catastrophic to the service, you know, a disk dropped off, service crashes, something like that in order for the FCI to fail. I've definitely had situations where I was using FCIs alone and I had to troubleshoot why I had a complete outage. And everybody said, well, I have an HA feature, why didn't it fail over? And said, because it wasn't checking for those things. So be cautious with the complexity here. This next and final diagram that I'll show you is about distributed availability groups. Now, I'm not going to get too technically deeper than them, but I wanted to show a really valid use case, which is when you're using infrastructure as a service in Azure, for example. But before I get to why that matters, let's talk about the structure here. You see I've got two different Windows failover clusters. They're on two different OS versions, 2012 R2 and 2016. I'm showing you that so that you understand that this is technically possible. You can span your distributed AGs between two different Windows versions. I don't recommend it. I'll go back to my earlier comment of you should make everything match as best as you possibly can, because that just makes everything simpler. However, this is a supported situation. And what you end up having is an availability group of availability groups. So this is kind of complicated, just like my last one. You're layering on top the feature twice, to where on the left side you have replica A and B. They're their own independent availability group. It has its own AG name, has its own listener, has its own everything. Same thing on the right side. C and D are their own independent structure. And then distributed availability group says, I'm going to have the primary of one AG write data to the primary of the other AG, and then things will cascade down from there. Now, this is useful potentially for the OS version thing, but more importantly in my case, it's for reducing egress charges in Azure. So in Azure, if anytime you send data into an Azure region, it's free. Network charges doesn't exist. But every time that you have data leave your region, that costs money. And it's the region that matters, not just outside of Azure. So if you're moving data between one Azure region and a different Azure region, even though it's still within the Microsoft ecosystem, it's now going to cost you some money. So what distributed AGs does is it limits the number of duplicate streams that you're going to have down to one. So previous architectures, you'd have A replicating to C, D, and B. Because it's important to understand that these secondaries are not peers. They're all secondary. They all come from the primary. They don't talk to each other. In fact, some of their DMVs and the information that they have about each other is limited compared to if you were to be querying the primary, for example. So in this architecture, if we didn't use distributed AGs, you'd have a stream going from A to C and from A to D. And that would mean that of your transactional throughput for your primary system, you have to double that volume of data and pay for it because you have two streams. So one use of distributed availability groups is to reduce that stream. You can bring it down to one. You only pay for your data egress once between regions as opposed to doing it twice. The failovers are a bit more complicated. I'm not going to get into exactly how at the moment, but there's additional effort, and it's definitely not a one-line of T-SQL like normal availability groups are for the failovers, because you have to manage the fact that you have two different listeners routing traffic to each other with their endpoints, and the failovers become a much more complicated thing for you to prepare for. It can all be scripted, of course. Anything can be, automated, scripted, and practiced, but it's just another layer of complexity that you wouldn't necessarily have if you just had a single availability group by itself. Okay.
Now, Simon has a question on the Slack channel. As it is supported, like mixing 2012 and 2016 Windows Server operating systems, would it be the right way to upgrade or migrate?
So that's a good question. It is a way to upgrade or migrate, and I definitely have nothing negative to say about that methodology, but there is other methods as well. There is a way with just availability groups themselves to where you can have one node, a different operating system, temporarily. It's definitely not supported to run full production, but it is supported for rolling upgrades. So I would look at it, Google it on books online. The process is very well documented, and you do not necessarily need a distributed availability group in order to do the rolling upgrades. There is a mechanism available for you.
Right. Okay. Although I do have personal opinions about Microsoft's cluster rolling upgrades, but I'll save my opinions later.
All right. Any other questions?
Not at the moment. I think you're doing really great.
Awesome. I think we're doing good on time and pacing too. So on the next slide, we're going to start talking about less of architecture and diagrams and more about features and lessons learned. So on the screen here, we've got this, this F-18 in fine working order. It's been polished up nice by the detailers. And what this is up here to show is a story. When I first began implementing the availability groups back with version 2012, I worked at a company that had a really hard time understanding the need for disaster recovery. So we would talk about it and they would say, yeah, DR is really important to us, high availability is really important to us, but they always meant at the hardware level. They always meant, well, yeah, if my server drops off, or if my VM host drops off, or if I have a power failure over here. They always meant these very localized kind of individual failovers, which HA can handle. But they never actually wanted to discuss the big stuff, like what if my data center was wiped off the face of the earth? Now, this was in Virginia. We're far enough away from the coast where hurricanes weren't really a problem. There's kind of mild weather down there, so nobody seemed to resonate with any of the real-world scenarios that could happen until 2014, when this jet crashed 6 miles from our primary data center. So we, in Virginia, there's a lot of military down there. We happen to be a number of miles away from the Oceana Naval Base, and this F-18 took off and immediately had engine failure as soon as it got up in the air and ended up crashing down into an apartment building. And while the event itself was tragic, I end up using this over and over again to remind people that there's a million scenarios that can cause disastrous failure for you that you're not thinking about. None of us were thinking about a potential plane crashing into our data center. I like that. And so in this case, it was awesome because after that, my life was easy. Every single meeting was like, all right, now let's talk about what happens if a jet crashes into the building. And then disaster recovery talks became a lot more serious and it resonated with people. I've only actually worked for 3 different IT companies so far in my career. And of them, 2 of them have had near misses like this. So one of them was this one. And then my current organization, we have one of our data centers in Philadelphia. And a few years ago, a crane collapsed on a building that was some number of blocks away. I think it was something like less than 10 blocks away. So these can happen. If that crane had crashed on the wrong building, then our entire primary data center would have gone out and we would have had to worry about a disaster in order to recover from. So don't just think small scale, also think of the big scale. Make sure you've covered yourself in multiple layers. And this feeds us into quorum. Now, quorum in this regard is a Windows clustering concept that I'm talking about here. And it's a voting mechanism. It basically tells the cluster that I know who is the true cluster, who's the real Slim Shady, basically. What it's trying to say is that it never knows that other servers are down. The only thing that the cluster can ever do is know that it can't communicate to them or hasn't received heartbeats from any period of time. So because it doesn't know that they're down, it needs to prevent what's called split brain. And split brain is when you have, let's say, an even number of servers. All of my architectures I showed you had even number of servers, by the way. So if you had 4 servers and something very common happens, for example, the network goes down between your primary and secondary data center. So not even a real disaster, something that I've seen millions of times. If this happens where network drops out, the servers in both the primary and the secondary data center don't know that the other ones didn't shut off. And both of them may want to be the cluster. And there might be resources that, like IP addresses, they're both trying to use. There could be a whole bunch of mess. But the way Windows Server works, it doesn't allow it to happen. If there's ever a situation to where split brain is potential, the whole cluster services will just shut off. So quorum is there to try and rectify this. Quorum's trying to say, I know who is the primary so that all the secondary nodes can shut off in this situation. And it does this by voting. Typically you have like what's called node majority, which is where you'd want an odd number. And you want that odd number to be in a situation to where if you lost, let's say, 2 out of 5 of your votes, that's no big deal. The 2 that can't talk to the other 3, those will shut their own cluster services off. The 3 that are talking to each other and know that they have the majority, those stay online. Your cluster stays online. Things will fail over properly to the majority half of the cluster, and then when communication comes back up on the other 2, everything will just kind of normalize. Now, voters aren't just servers, though. Voters can also be file shares. They can be remote shared disks. They can also even be cloud witnesses. I don't have that on my slide, but you can also use Azure, for example, as an external witness. And you always need to make sure that you weight your votes appropriately. So let's talk through a couple scenarios of this jet. Let's say I were to have 2 servers in my primary and a file share witness, and then 2 servers in my secondary. Well, if the jet comes in and crashes into the primary data center, we already knew that we'd have to do some form of manual failover to get to the secondary. But we now have to add a second step to that process. And the reason for that is because the 2 servers remaining in their secondary site now think that they're the minority in the cluster because they lost communication to the other 3 votes, which means they shut off their cluster services. So a cluster that you thought would be online for your DR is no longer online. And it requires manual intervention to do what's called forced quorum, which is where you take the responsibility of declaring that these servers are good and can bring them back online. Now it's just another step, and if you're already doing a manual failover, maybe that's not a big deal for you to add into your DR plan. But it's better to avoid that. So let's flip the scenario. Let's say instead your primary data center only has 2 servers, your secondary has 2 servers and a file share witness. Well, in that regard, if a jet hits the primary, then you don't have to force quorum, right? But am I recommending that? No, I'm actually just showing you a whole bunch of different problems, no solutions at the moment, because let's go back to my network drop scenario. In a situation to where your secondary site has more heavily weighted votes and the network blips, then your primary data center goes down. Because of a network outage to your secondary site, now you've just lost your primary data center because the cluster services will shut off thinking that they're the minority. So what's the solution, right? Well, one solution is to use that cloud witness I just mentioned. So if you're using Azure as your cloud witness, now you have 3 physically, geographically separate voters. And if anything happens in your primary or secondary site, whichever one is still functional will be able to view the witness in the cloud. And that solves the problems that I just mentioned right there. In addition to that, we have a few kind of slick features with Windows Server that I'll talk about now. The first one's called Dynamic Witness. And Dynamic Witness is, all these features, by the way, are only Windows Server 2012 R2 and above. And you should be on 2012 R2 or above anyways, but I figured I'd have to say it because I know there's some 2008 servers out there somewhere. So with Dynamic Witness, what it is the system is going to remove votes from voters as it feels appropriate in order to prevent the potential for a split brain event. So in this case, we've got 2 servers in the file share witness, and we've got total votes of 3, total owners of 3. Now there's an intermediate state where server B, for some reason, can't vote. Whether that's because it couldn't send its heartbeats fast enough, whether the network actually dropped, where the server is actually down, whatever it is, it doesn't matter. All it knows is that server A and the file share don't know it exists anymore. So at this point, you now have an even number of votes, a file share and a server. And because even numbers have the potential for dividing in half, the server doesn't like that. And that transitions into the dynamic witness feature kicking in and removing the vote from the witness. So the witness will always be the default loser, because it's seen as less persistent than any other server, for example. So here we now have total votes of 1 and online votes of 1, because it not only removes the vote to make it a non-number, but it also recalculates the total so that you don't become the minority. If the total remained at 3 and this happened, well then server A would only be 1 out of 3 votes, and then the cluster server should shut off on server A, and that's not good. So that recalculation is really important. And then the fact that votes can drop offline is equally important. The next feature we're going to talk about is called Dynamic Quorum. It's extremely similar to the Dynamic Witness. The only difference is you can continue to cascade further, especially if you don't have a witness. So in this case, you have 2 total votes, 2 online votes. Dynamic Quorum is going to immediately step in and take a vote away from server A. Now this kind of highlights the fact that there's no problem with server A at this moment. It is fully online, it is a fully functioning part of the cluster. You can fail over to it just fine. There's absolutely no problems here. But it's removing the vote so that if something were to happen, if network between A and B were to be lost, the cluster knows in advance that B is the winner, that B will end up being the cluster service that stays online, A's cluster service will shut off, and you never have a full outage in that regard. The last feature I'll show you is Tiebreaker. Tiebreaker is the ability to lose 50% of your cluster, not 49%. So Windows Server 2008 R2 and below, if you lost more than 49% of your cluster, all cluster services would drop because you'd end up being in either split brain or minority situation. Well, what this does is you have a parameter that you can only view and manipulate through PowerShell called lower quorum priority node ID. And this declares which node is the one that dynamic quorum would act upon when the need happens. So when dynamic quorum has to pull a vote away, what node am I going to pull it away from? By default, the value is 0, and 0 means the lowest ID value, which is arbitrary. I mean, the order of the ID values in your cluster is based on when you added the nodes, not based on whether you actually wanted them to be those numbers. So in this case, I've got server A is ID 7, and server B is ID 2. But you'll notice I mentioned that by default it does the lower ID. So why did it pull the vote away from A? And the reason for that is because you can explicitly set it. So after you build your cluster, you can look at your ID values and say, I want my DR site to be the default loser. Therefore, I'm going to set a node in my DR site, its lower quorum priority node ID to whatever that ID value is. So now, if you ever lose 50%, like if you had 8 nodes and you lost 4, it stays online. Less than a couple seconds later, it's going to recalculate the total to 4. You could lose another half, so 2 more. It'll recalculate again, you could lose another 1. And that's what allows you to have last man standing, which is the ideal situation for a cluster. It's still not perfect because you can't have a catastrophic failure. You can't lose 5 of 8 and have it stay online, but at least it's a lot better than it used to be.
And that's probably the response that Gordon was asking. His question was, I'm never entirely sure what happens to a cluster when you have 2 or even 1 server online. That's probably the answer he was looking for.
Yep, exactly.
And another question from come on, where is that? Sri, if we use the files or the file share as the quorum type and it's on the primary data center, how does it work? Will it be able to switch to secondary?
So witnesses are very easy to move. I mean, technically they're a drop and create situation, but it's very easy to reconfigure. So if you were to have your file share in the primary, through the Windows Failover Cluster Manager, it's very easy. You just remove the witness and then add in a new one. It takes seconds worth of time and only a couple dozen clicks in order to make it happen. So it's a pretty easy move, but there's no like migration concept. It's just get rid of the witness and then make a new one.
Actually, the concept behind the quorum is the most complex, convoluted, complicated, confusing topic ever. But a lot of people don't realize that this is the most important concept that makes your failover cluster highly available. In fact, I spent a lot of time on my training class explaining just how the quorum behaves. But
you're exactly right. It's really important, and that's why I devote a bunch of time in the session to it, because most people don't even know what it is. And I at least want to give people enough to go research it and enough to say, I understand why this is so important. Let me go figure out this extremely complicated and very large topic. All right. Any more questions before we move on?
Not at the moment.
Okay. Thank you. All right. So now let's dive into a couple of the more fun features of availability groups. The first one I'll talk about is you can achieve faster failovers. Now, technically, it's not faster than everything. So I know one person in the past has proven to me that database mirroring could actually fail over faster than the availability group in some cases. However, what I'm referring to when I talk about faster failovers with AGs is everything to do with the client connectivity and the DNSing. So this is specifically for multi-subnet failovers where you have multiple IP addresses. Now, if you fail over within the data center and that IP address in the same subnet, then no big deal. Your client applications will have cached from the DNS servers the IP address. Their connection will break when the failover happens, and then it will come back up X number of seconds later when the failover completes. And the next time the application tries to connect, then it will be successful. However, when you cross subnets and you have a different IP address, this becomes, another piece of time that you have to worry about. There's a thing called TTL, time to live, on your DNS A records, and that's a caching mechanism so that every connection that ever happens doesn't, slam your DNS servers like crazy. So most companies I've worked at either have it set to like an hour or 20 minutes, depending upon what their policies are. And what that means is if it's 20 minutes, for example, you would do a failover to your secondary site. The database might be online in 30 seconds. But the client application will be trying to connect and failing for 20 minutes, waiting for its cache to expire, which means you have to put in some complicated steps into your DR plan to make sure that you flush DNS cache on all of your clients, and then you always miss some because somebody made a new app that they didn't register in a DR plan. There's always a lot of hassle there, and it significantly impacts your recovery time objective, how fast you can do your failovers. Well, the way availability groups work by default is you'll have a listener and you'll have multiple IPs, and that listener will register multiple A records for the same virtual network name for each one of the IP addresses. This makes it even more complicated because if you don't use the parameter I'm about to describe to you, what will happen is every time the client tries to pull down an IP from the DNS server, it'll semi-randomly pick either one of the A records. And the one it picks may or may not be the one that is actively in use at the time. Remember I mentioned earlier the listener is handling which one is online and which IP addresses are offline. If they're offline, you can't connect to them. What this causes is an amazing amount of troubleshooting hassle to where everybody sees intermittent connectivity and feel like the system's unstable, when really the system is stable. The problem is that the client provider is caching a different IP address each time and causing you some problems. And that's where this parameter comes in. So multi-subnet failover equals true comes from the need for the provider to handle multiple IP addresses being registered for the same name. And what it will do is it'll cache all of them. So if there's two, it'll cache two IPs. And then what it will do is it'll try to connect on both of them simultaneously. And the first one that connects wins and abandons the other connection. Because the listener makes sure that only one is ever online at a time, you never get a scenario where you connect to the wrong one. It's always going to be to the correct one, and it's always going to be whichever one's online. So what that means is when you do a cross-subnet failover, the DNS cache, it can still do its job and not beat up the DNS servers with continuous attempts to get new IP addresses, but you get none of that time to live lag affecting your RTOs. Now the caveat here is that you have to have a fairly up-to-date provider for this. For example, .NET 4.0 and above providers, JDBC 4.0 I believe as well. There's a whole list of supported providers, and nowadays they're pretty common, but I know for a fact legacy systems still use some old versions of providers that don't have this parameter. So you have to be very careful when implementing the availability group to know that everything that connects can use this, or else you have to go back to the old way of doing things. And the old way of doing things would be to modify the cluster register all provider IPs parameter to false. What that means is that the listener will no longer register 2 A records. Instead, it'll register just one, and during failovers, it'll maintain it, meaning it will update the A record to a different IP address. But that puts you back into the exact same scenario where you have to manually figure out how to handle your DNS caches yourself. You have to flush them during DR, failovers, and things of that nature. So if you're using up-to-date providers and you use this in your connection strings, then you get faster failovers because you take the DNS caching challenge out of the mix completely and just allow the listener to handle that for you. The next feature here is read-only routing. Now this is, other than the basic HADR of availability groups, this is my absolute favorite feature of the entire system because it allows you to offload your reads and your backups to a secondary system. Now we're not going to dive too deeply into the backup concepts here, but I will mention that you can offload full backups that are copy only, and you can offload transactional backups in their normal state to your secondary replicas. You cannot offload differential backups. In my personal opinion, doing the backup offloading complicates the management of backups significantly enough that I tend not to recommend it. I tend to still prefer the primary. However, if you're in a situation to where running backups in your primary is that much of a significant hassle to your performance of your system, you could do it, or maybe look into why you're undersizing your hardware instead. But as far as workload offloading, this makes a lot of sense, partially because when you offload your reads to your secondary site, your secondary replicas, you are also implicitly forcing all of the transactions to run under snapshot isolation, which is an optimistic locking mechanism, which is really great for removing blockers. I'm not going to get into a lot about the isolation levels and their caveats, but it's definitely something to look into and to understand. If you're using availability groups, know that you are changing from read committed over to snapshot whenever you read-only route to your secondaries, and then understand the benefits and potential pitfalls of that. The way you'll use read-only routing is you'll pass in application intent equals read-only into a connection provider that supports it. So again, you have to have some fairly recent connection providers to do this. And then the listener is going to manage this. So you're always going to connect to the listener, and this has to be through the listener. And then what's going to happen is it's going to reply back with the necessary information for routing you. So here's an example of one of the DMVs I wrote a query for showing the routing list. You have to configure this yourself. It's not automatic. So you have a routing list, and you'll say things like, when this is primary, go to this secondary. When this one's primary, go to the other one that's secondary. And there's a routing priority list with the endpoint URLs all stored in here. This is T-SQL. It's not that hard to implement, but it is something that you do explicitly. On pre-2016 servers, you can only go to one secondary, meaning you just tell it to go to the next one. If that's not available, it will go to the next one. However, in 2016 and above, you can loop in some round robining. There's a lot of criticism where this isn't really load balancing, and I don't think anybody ever said it was, but people wanted it to be some load balancing, I guess. And in 2016, you got the ability to at least round robin across your multiple read-only replicas. And that still doesn't assess load in any way, but at least it spreads the load across whatever readable secondaries that you have. Now, you must also connect to the availability group database itself. Now, this is something I haven't touched on, but it's really important, is the listener is managing this, but because you connect to the listener, it doesn't imply that it's going to be utilizing the availability group features. You have to actually, when you connect directly to a database within the appropriate availability group, and then the listener will utilize read-only routing. If you don't do that, you'll do what I did, which is spend a couple weeks in the beginning trying to figure out why read-only routing always sent me to the primary. And that was because I was using default connection to master. So just because I went through the listener doesn't imply that I'm going to go to the secondary replica. It has to know which availability group to look up, because when you're connecting in, depending on which database you pick, you could have multiple availability groups with different routing tables. So careful of that pitfall, especially if somebody's complaining to you that they're never on the secondary replicas. So now there's a little bit of a connection overhead that goes into the routing. What will happen here is the application intent parameter gets passed in from the client, goes to the primary to the listener. The listener is going to reply back with the endpoint URL, and the client is then going to move itself over to the secondary. So it's important for you to understand your routing tables, because you don't want to do what I did, which was I had set it up, this was pre-2016, so there was no round robining. I had set it up to where if my primary went down, it would go to my secondary within my data center. If that one was down, it would go to my secondary data center. Well, this became a problem the first time I said, I can do some online maintenance. I don't actually have to take down and have this big outage window. I'm just going to do maintenance on my reporting replica, and when it comes down, it's going to just have everything go back to the primary, because by default, when it exhausts its list, it goes back to the primary. Well, but my list wasn't exhausted. So instead what happened is it took time to connect to the primary, and then it took time to try to connect to the secondary. Then the secondary timed out because it was down. It took more time to go to the DR site because of a high latency network connection. And by that time, the application timed out. Its connection timeout was really small, and it just said, oh, nope, I'm done. So what I did, by taking down what I thought was a safe replica to remove, I caused a functional widespread production outage because the entire system would no longer function. So be very careful about how long it can take for your secondary route to happen based on latency, and also work through what does it mean if it fails to connect to that? What's the timeout, and how does that add into my connection time for the application itself? So be very cautious about that. And with this, we're kind of wrapping up. We only got a few minutes left anyways, and I want to try to take a question or two. This is a list of references that I think are really important from this point forward. So anybody who, was at the right pace for this session, these are the important next steps for me. The top one synchronizing the server objects, which you should look into because you need to automate it, and this gives some really great community examples of how to automate it. The second one is a PowerShell desired state-driven failover test. What it will do is automatically reconfigure your asynchronous routes between your data centers and make them synchronous, wait for everything to catch up, do a failover, then reconfigure it back. And this is really useful for like quarterly or annual tests that you're trying to do. The next one is a way of kind of hacking SSMS to store the multi-subnet parameter for you and the application intent parameter. And then another one is kind of like a huge red flag. If you're going to use file stream in availability groups, read this. Paul Randall helped me through a production issue a number of years ago, and this article is kind of the brainchild of him and my problem. You can have some disastrous effects with the garbage collection of file stream when combining it with the lazy log truncation that availability groups use. And then finally, there's a 7-part blog series that gives you the how-to that I didn't give you today. So with that, if you have any questions, I'll take them now. And if you also don't mind, please go to the feedback link I have right there, sqlhammer.com/go/feedback, and let me know what you thought of the presentation.
I do have a personal question for anybody who's in the attendees. How many of you actually used read-only routing in your configuration? Just curious. I mean, you could type, yes, I do have that. Yes, we implemented. Yes, I made the same mistake as Derik's. I'm just curious. There is a question on Slack channel 3. Can we do the backups on all servers? Set all servers priority to 50-50, 50-50. I don't know what that means because that does not add up to 100.
I think, yeah, 25, 25, 25, 25 maybe.
So if I'm understanding the question correctly, if you set everything to the even weighting, there's still like a prefer secondary or prefer primary settings in there. So you're going to have to do something like that. You're either going to have to weight things appropriately to where it knows which one to pick, or you're going to have it prefer, you know, which side of the house you want, primary, secondary, or things of that nature. I find that the backup offloading becomes extremely complicated because all of your history is now spread across multiple MSDBs. So if you're like me, I want to recover things very quickly, which means I'm always going to use some sort of dynamic scripting tool or something like that to derive my recovery scripts. I'm not going to, you know, write a diff, and then 10,000 log restore commands in order to try and get the database back online. So I kind of tend to advise against it because of the dispersed nature of your history into all the different MSDBs that aren't being replicated together. And then another one is the fact that you can really only do log backups the way that you expect to on your secondaries. You can only do copy-only fulls, which has some implications, and then diffs are just completely out of the picture. So my personal choice is I tried doing that for a couple weeks the first time, and I decided that it wasn't worth it, and all of my availability groups to date are just running backups off the primary.
Emily asked, and she said, you mentioned that you'd provide info on some of the server level object items. Is that in the links that are shown up on the slides?
Yes, definitely. So if you're talking about like the server level objects, as far as replicating them between cluster nodes, then the top link is what will get you there. If you're talking about DMVs and some other information, the very bottom one, the 7-part blog series with the how-to has a lot of that information.
Awesome. Well, thank you very much today for hanging out with us today, Derik. Really appreciate the session, and thanks, Edwin, for monitoring the questions there. Everybody give him a warm round of virtual applause.